I joined Edgar Allens in '64, and I started as a draftsman in a subsidiary company working on, well, basically industrial boilers, pressure vessels, mainly in that area, but I was also, because I'd previously worked in the furnace industry, asked to assist an engineer that specialised in magnets. Now, why heat and magnets? Well, basically he was doing research into the temperature effects on magnetism and looking at low temperatures particularly. The idea was several things. Considering I only worked with him for about 6 months, there's so much happened in that period. The main thing, like I said, looking at magnets, I designed and helped construct a plant that could go from plus 400 degrees centigrade to minus 200 degrees. And he was trying to find magnets that could work within that area. Now, one of them was one that at general normal temperatures, ambient temperatures, the material was not magnetic. But once the material dropped to around freezing point, it became magnetic. Now, as a coincidence, I later saw some of the test work on this material, because I moved that work. I was on Whedon Street. I moved onto Shepcote Lane, and I had an office at the side of the canal. And this gentleman, I can remember his name as John, but I can't remember just what his second name was. He set up a test facility along the side of the canal, and he had Russian visitors there, and he demonstrated these magnetic systems. And the idea was, his first idea was to put it on electrical transmission systems, the overhead cables. Temperature drops, cable warms up through the magnetism and doesn't freeze. But what the Russians wanted was something that they could bury and didn't freeze. So that gave them efficient power transmission right across Russia. They bought the rights to it, we didn't use it. So, yes, the rest is history, as they say. But at the same time, he was working on something else, which was magnetic levitation. The Japanese maglev trains work on the same principle. But whether he was an inventor or just simply somebody that's developing it, I don't know. But within his little laboratory, he had a method of floating aluminium magnetically. Now, aluminium is non-magnetic. And not only that, he could effectively fire an aluminium sheet at a target. Now, the latest development in military weapons is magnetic fired guns. They call them rail guns. So it's taken all this time to develop them, yet he had one running in his little laboratory. Right. Now, all right, that section of Edgar Allens which was called Industrial Pressure Vessels. That was closed down. Most of the work that we did was for a company that actually built pressure vessels and was another subsidiary of Edgar Allens. They no longer needed us, so we were shut down. And I moved across into Shepcote Lane, and my first job was a draftsman working on cutting tools. Now, I could talk for weeks on this, but that's beside the point.
What was
One of
sorry.
Yeah.
What was the shop floor like? What was the actual
Now, for the heat exchangers, it was in part of the old Edgar Allens foundry, and we had a big fabrication shop where I didn't see much of it. They fabricated the pressure vessels, heat exchangers, but across in Shepcote Lane, we were in the largest cutting tool manufacturers factory during the war. I was built specifically for the war, and there were a lot of things wrong with the design of the place, but it was generally a very clean factory. Some of the machinery was, I say ancient, but 1930s vintage, but a lot of it was quite modern and very precise. As I say, generally it was clean. The whole place, as far as the personnel were concerned, and particularly on the shop floor, was extremely friendly. Everybody knew everybody else. And there were about 120 of us in the factory at the time. As I say, it was the largest cutting tool manufacturers during the war, and they produced special tools for drilling armour plate. There's a very long story about that, which I will say, but the main material they used was called Stag Major, and not only did they make drills from it, but they made tools for cutting steel generally, mainly steel, but one or two other materials as well. It was a high alloy, high speed steel, and it was the only drill at that time that could drill armour plate. And one of the products on the two of the products on the Shepcote Lane side, one was railway joints, and they're still made on that site. And another one was liner plates, which are the plates within the bearing systems of railway trucks. And the material itself is extremely hard wearing because it was called work hardened. The more you use it, the harder it gets. So much so that I used to demonstrate to visitors, put a small piece of 12 to 14% manganese steel in a vise, file it, and then try to file it again, and it took the teeth off the file. And the other thing about this material is on railway work, you can imagine where a train is being diverted from one track to another. Call it 100 miles an hour. There's a lot of tonnage and a lot of wheels hitting these joints. and it comes down almost to a point where the joint is. So most materials just wouldn't last 5 minutes, but this stuff was guaranteed for 5 years. No replacement of that joint within 5 years. So that's what one of my main jobs became, how to machine that stuff. But as I say, to start off with, within the tools department where I started, there were two main divisions. One was the high-speed steel section. As I say, everybody was very friendly. People were welcome on the shop floor. Come down, have a chat and all the rest of it. I'm trying to think of any particular incidents, and I can't off the top, because it's a long time ago now. But the second section was making tungsten carbide. Tungsten carbide is, as it says, a mixture of tungsten and carbon bonded together with all sorts of other metals added in. It's the best description of it is if you are making a pie crust, mix the materials together and bake it, and they stick together without actually changing the materials themselves. The flour is still there as flour, milk is still there solidified, that sort of thing, or water dries out, and that's what tungsten carbide is. But it's modified in so many ways with other exotic materials like tantalum and vanadium and all sorts of things. As I say, there's a section that produced tungsten carbide, mainly cutting tools, but also wear materials. And that section was separated from the high-speed steel because you didn't want any contamination across. The tungsten carbide was cooked in a vacuum. So there's some very sophisticated equipment in there. And just this one really is an aside. In Germany, Krupp were making tungsten carbide in the 1930s. But what very few people realise is that it was copied from Edgar Allens. Edgar Allens were the first to make tungsten carbide. And in many cases, Edgar Allens did not protect their developments and inventions. It was a great pity because this company would still be going. From my point of view, my main job from being a draftsman was designing cutting tools and becoming development engineer to cover cutting tools, yes, but all sorts of processes. And through that, on the Shepcote Lane site, there was the trackwork division making trackwork joints, which is how I got involved in trying to machine the stuff, and liner plates. On Sheffield Road, there was a small section that made what's called hot saws, and therefore cutting steel hot as it comes out of the rolling mill. Now the saws we made were up to 7 feet diameter, and they were made in such a way that they could run so that the periphery, the outside edge, could be run at 30,000 feet a minute. I won't describe the process, but if you can imagine a steel beam, in those days it was a yard deep, 36 inches, being cut in 10 seconds as it comes out of the rolling mill, still hot. That's what the hot saw was for. Right. Yes. Going back to the tool department, because I'll have to come on to the track work, etc. later. And the tungsten carbide in particular, we had an absolutely brilliant metallurgist who was world recognised, and he came up with the idea of two main things. One of them was, instead of producing high-speed steel by the melting processes, melting and forging to produce high-speed steel, because he'd got all the experience of tungsten carbide, which was produced by a powder process, he started to apply powder metallurgy to high-speed steel. Now we managed that, and between the two of us, we went into production with powder metallurgy, high-speed steel. But also, he came up with the idea of producing high-speed steels that literally cannot be made any other way. There's a certain diagram that shows the stability of materials according to their contents, and he developed ways of coming out of this so he could make steels that were stronger, mainly in tension, but also harder than any other steel.